Hi, hello viewers. Alright, welcome to today's episode. Okay, on the board here we have some equations on the board, some chemical equations on the board. Now, what are we asked to do with these chemical equations? We are asked to identify whether each of these reactions has a negative entropy change or a positive entropy change. Now, before we start analyzing the entropy change of these chemical reactions, we have to ask ourselves, what do we mean by entropy change or the word entropy? The word or the term entropy simply means the degree of disorderliness of a system. So when a system is more disordered or more scattered, it has a higher entropy. When a system has less disorderliness, it has a low entropy. Now, entropy change means moving from a more arranged to a less arranged system. So if a system is more scattered and then it moves to more orderly, then it has a negative entropy change. But when a system is less scattered or less disordered and then it moves to a more disordered system, it has a positive entropy change. Now, the first equation here on the board is sodium chloride and sodium chloride. How do we tell? Now, if you look at this, you find out that the state of this sodium chloride is solid, while this is what is in an aqueous state. Now, what does this simply mean? Solid states are more ordered, they have less entropy. But when this particular sodium chloride is dissolved in water, it is now in an aqueous state, which means it is more in a disordered manner. So from less disordered to more disordered, that is more scattered, it means that the entropy change is positive. It has more entropy change. So from solid to aqueous state, the entropy change here is what is positive. Now, how about chlorine gas and chlorine gas? Now, in this case, gases, we know they have more entropy, or their entropy is more scattered, right? The system is more disordered. But how do we now tell if it's a negative or a positive change? Now, if you look at this, we have just one molecule of this chlorine gas, and on the other hand, we have 2 molecules of this chlorine gas. How do we now tell? We can tell that by saying that one disorderliness gives us 2 disorderliness, meaning 2 scattered system. So mean that this is more scattered than this, right? So from one gaseous state to 2 molecules of gaseous state, it means that the entropy is positive. We have more disorderliness in this system. Now, what about this? In this reactant, we have nitrogen and hydrogen producing to give us ammonia gas. Now, on this reactant side, we can see that all the species here are in the gaseous form. But in the product side, all the species here are also in the gaseous form. How do we now tell? The product side have 2 molecules of this gaseous species, and the reactant side have 2 plus 1, which is 4. So on this side, we have more disorderliness, but as it moves to the product side, the disorderliness is reduced to what? To 2. So in this case, the entropy change is now negative because it is reducing, right, in its degree of entropy. So in this case, the entropy change is negative. Now, what about this? We have hydrogen gas combining with an iodine gas to produce hydrogen iodide. And on the reactant side, they are all gases, and on the product side, they are also gases. But how do we tell? The reactant side have 2 molecules of these gases, which means there are 2 molecules of disordered system, and on the product side, same 2 molecules of a disordered system, which is in the gaseous state. So what is the change between the reactant and the product? Talking about entropy. So in this case, it is neither a negative entropy change or a positive entropy change. Instead, the change here in entropy is neutral. So here is what is a neutral. There is no change in both the entropy of the reactant and the product. If you like watching this video, or if you have learned something today, make sure you subscribe to this page, like and follow this page. Bye for now.